All right, I think we should be live. There's a school closure today because of inclement weather. So, uh, because time is too precious to waste, and because we have a lab that it's very challenging to reschedule on Friday, we kind of have to move on with these lessons. So I hope you find this recording useful. Most of this is actually review, to be honest. So you should be able to do this even without this recording, but hopefully, if not, this is a good reference for you. Today's lesson is stoichiometry with molarity. We've done a whole bunch of problems with stoichiometry previously, and molarity is something that we did in the first trimester. So we're just combining those two topics today, and we'll incorporate this knowledge into a lab on Friday. And actually, we'll be using some of this stuff for labs the following week after that as well. So a very important lesson, but again, also review in some ways. So let's jump right into it. These notes will be provided at some point, but hopefully you can follow along or pause the video when you need. This is kind of the warm-up. You might recall that we investigated molarity way back in the middle of the first trimester. We define molarity. Molarity is defined as moles of solute. So you might recall, I guess we should have talked about what it's used for. Erase this. Moles of solute per liters of solution, and we use it for concentration of solutions. So you might recall a solution is a mixture of two or more components. And when we're talking about mixtures, we care about how much stuff is in the other thing, right? What are the ratios of the things? And molarity is just one way that we can talk about concentration. The solute is the thing that's dissolved in lower amounts, and the solution is the total mixture. And so this I'll kind of write to the side here. This is the component in lower amounts. Typically is how we define it. And you may recall that the units of molarity, I guess I'll write it here. Units of molarity are big M. Right? These are the units. Right? We read that as molar. So in example 2 here, the 0.788 capital M would be read as 0.0 or 0.788 molar solution of sodium hydroxide. Okay, so let's now that we kind of have hopefully refreshed our memory on what molarity is, let's jump into a calculation using molarity. So this 0.788 molar solution, that's kind of our starting point here. So this is our molar solution of sodium hydroxide. And the key here, the problem is asking for, hey, how many moles are present in this volume of solution? So if you want to draw a picture or something, you can let's do that to the side here. So if you want to draw a picture or something, you imagine that you have some bottle, all right? Some bottle of liquid here, the sodium hydroxide, some volume in there, and the bottle is labeled as 0.788 molar. All right, and you're going to pour some out. You're going to pour some out into a beaker. All right, you're going to transfer some into a beaker, and the volume that you're going to pour out is 475 milliliters. A couple things to kind of note here. One, no matter how much you pour out, whether you pour out a little bit or a lot, the concentration is going to be the same. Right? The analogy is that if you pour out some orange juice, the orange juice that's in the bottle, the original bottle, is going to taste just as sweet as any amount that you might pour out into a glass, right? Whether you pour yourself a small glass or a large glass, the concentration is the same. right, of sugar. That is, it should taste the same regardless of what container it's in and what volume you pour out. The difference is that in this big bottle, there's more sodium hydroxide. If you pour out a little bit, there's going to be a little bit less sodium hydroxide, right? But the concentrations are the same, so that's something to keep in mind. Okay, so I'm going to rewrite this, right? Based on our definition of molarity, we can rewrite this as 0.788 moles of sodium hydroxide per 1 liter of solution, right? So if I had 1 liter of this solution, I have 1 liter of this 0.788 molar solution of sodium hydroxide, there would be 0.788 moles of sodium hydroxide in that 1 liter. Again, we are not pouring out a whole liter, right? We're actually pouring out just 0.575 milliliters. Because the units on the bottom of this thing here, right, because down here this is in liters, well, we probably have to convert the milliliters. Well, actually, instead of doing it by mental math, I'll show you the conversion. Instead of working with milliliters, we want to work with liters. So I'll convert this to liters. So there's 1,000 milliliters per 1 liter. So this is 0.575 liters. Okay, so I've done all the conversions and I've rewritten things as I need. And so let's go ahead and do our calculation. So if I take 0.788 moles of sodium hydroxide per 1 liter of solution, I'll move some stuff over again. I don't know if that picture is actually helpful for you, but it's there. And then we're going to multiply that by our volume that we're pouring out. So 0.575 liters. You notice that the units of liters here cancel out. And we're left with 0.453 moles of sodium hydroxide. So in that 575 milliliters, that's the number of moles of sodium hydroxide that would be present. Right? So, really, this is just to reiterate that this is a way to figure out the number of moles that are dissolved in some amount of solution. Now, we've done a bunch of problems with stoichiometry where we're working with moles, and it should be no surprise to you that if you're going to work with solutions and work with stoichiometry, the first step is probably just to convert to moles, or maybe convert to moles later using the concentration. So let's look at some example problems really quick. There's some more classwork problems I hope you work on. Those are due some point tomorrow. Hopefully you find time to work on some of these. Okay, so we read through this problem here. Maybe I'll drop this down a little bit. Just pull that down, separate it from all the other stuff. Just give ourselves a little more room. Okay. All right. There's a stoichiometry problem. So as always, we do our thing where we write our chemical reaction out. That's our recipe. So we have zinc plus hydrochloric acid. And that tells us goes to zinc chloride. You might recall zinc chloride has a 2+ charge, and chloride is a halogen with a -1 charge, so it should be ZnCl2. And then we also form some hydrogen gas. Hydrogen is a diatomic, so we write it as H2. Right? So we write all our species out, and then we go ahead and add in our stoichiometric coefficients. By inspection, I can kind of tell that this is going to be 1, this is going to be 2, and then this will be 1, and this will be 1. So everything looks like it's balanced. So let's go ahead and begin constructing our ice table at business as usual. Right? Now, there's something that I'm going to allow from this point forward, which is when you read through the problem, if there's certain boxes in the ice table that you don't need to fill out in order to answer the question, then just don't fill them out. In this specific example here, it's asking for the amount of the starting reactant that we need. That is, in order to get rid of, let's say we have some pile of zinc, some 12.35 gram pile of zinc, and we're going to pour some hydrochloric acid onto it in order to fully react all of it. Well, it doesn't actually ask in this problem for how much product we make. And so we don't care. And so these two columns are actually not really relevant to the problem. Sure, you could fill them out. This problem has more than enough information for you to fill that out. But we don't need it to answer the question. And so if you read through a problem and you determine that there's some columns that are not relevant to answering the question, from this point forward, you can go ahead and leave them blank or just kind of cross them out. Okay, now back to the problem at hand. We read through the problem, and it asks for the amount of hydrochloric acid we need in order to react with 12.35 grams of zinc. Right? You probably remember that in ice charts, we always want to have the numbers that we plug in are always moles of stuff. And so we're not given any of that information yet. We're given a concentration. We're asked for the volume of this solution that we need, right? But we're not given the volume of it, so we can't figure out the number of moles. But if we look further ahead, you see that we're given 12.35 grams of zinc. So we can convert that to moles. So maybe we start with that. So 12.35 grams of zinc. I'm going to convert that to moles, so we pull out our periodic table. You will probably find that zinc, for each mole of zinc, that has a mass of 65.38 grams. Let's double check that I did that correctly. Yeah, 65.38. Okay, so multiply that through, and we should get 0.189 grams of zinc. Oh, sorry, moles, excuse me. Sorry. Erase this. Moles of zinc. And I'll go ahead and plug that into my table. 0.189. Now, this problem, we can also make another assumption here. That is, because we're going to fully react both the zinc and the hydrochloric acid, we can assume the end amounts are going to be 0. Right? So that's what we can assume. Now, if the initial amount is 0.189 moles of zinc, the end amount is 0. We know that the change in this column is going to be negative 0.189. Right? Nothing new there. I'm going to put a little green thing here just so we know where that number comes from. Okay. Based on our ratios in the table, maybe I'll use a different color here. Based on our ratios in the table, we know that this should be negative 0.378. We knew that the end amount is 0, so this must be 0.378 moles of HCl. Okay, so in the problem, we kind of need to figure out the number of moles of HCl. Well, we do need to figure out the number of moles of HCl that we need, but that's not the answer to the problem. The problem is asking for the volume of some solution that we need to pour out. So you imagine that you approach a bottle of hydrochloric acid, and the bottle is labeled as 3.00 molar. And you need to pour out enough to get 3.78 moles of it into a container so that you can then go and react it with 12.35 grams of zinc. That's the visual. Now, if we want to pour out 3.78 moles of HCl, we can use our concentration as a conversion factor. But I'm going to flip it this time, right? Because we want to convert to volume. So we know that in 1 liter of this solution, we have 3.00 moles of HCl, right? So this number comes from the concentration. So I'll kind of highlighted that, right? This is the information that came from the problem. So I multiplied this through, and I end up with 0.126 liters. Problem wants it in milliliters, so let's go ahead and convert. So we get 1.26 liters, and we're going to multiply that by 1,000 milliliters. That's a going rate, right, per 1 liter. and this is equal to 126 milliliters. And this is our final answer. Right? So in order to react this whole pile of zinc, this 12.35 gram pile of zinc, you would need to pour on 126 milliliters of this 3 molar solution of HCl. Let's do one more example problem. Again, we want to write down our balanced chemical reaction. And so this reaction tells us we have copper that is reacting with silver nitrate, HeNO3, as you might recall, if you remember polyatomic ions. And then that goes to silver, metal, right? This is a redox reaction. And then we get copper to nitrate. Nitrate is a -1 charge, so we need 2 units of that to match up with each of the coppers. Reaction's not balanced yet because we have we don't have enough nitrates on both sides, as you can see. So I'm going to put a 2 right here, a 2 right here, and then everything else should get a 1. We can construct our ice table again. And reading through the problem, it looks not too dissimilar from the problem we did before. But it's asking us to maybe go the other way, right? So it's asking for the number of grams of copper that are needed to react with some amount of this solution of silver nitrate. So you pour out some silver nitrate, we need to figure out how many grams of copper we need to weigh out in order to react with it. Again, reading through the problem, this is very similar to the last problem where we don't care about the products, but note that in problems you'll do for the classwork, it might not be that you might be concerned about the products, right? That is, you might not be able to cross out these specific columns. You just have to read through the problem and determine what's relevant for you to answer the problem. All right. So here, I'll highlight again this information over here, right? That's some information that we can maybe extract to put into our ice chart. So let's begin. So here we have a 50 milliliter solution, and we have a volume, and so concentration. And so with the volume and the concentration, we can figure out number of moles. That should be no surprise to you. So we have 8.0 moles of silver nitrate per every 1 liter of solution. And if we multiply this by a volume, we can convert to moles. You might recall that we did something like that up here in this problem. Right? And so hopefully by now you're comfortable with converting between milliliters and liters. So I'm just going to do that without showing my work. Apologize if you need to see it, but you just basically divide by 1,000. Right? So 0.0500 liters. Units will cancel out here and here, and I should get 0.40 moles. I'll plug that into here, 0.040 moles. This problem, again, reads very similar to the previous one, and so we know our end amounts are going to be 0 and 0. They don't really have to be, but it's an assumption we make because of the way the problem is stated. We're just basically trying to determine the bare minimum of each reactant that we need to fully react both of them, right? What is the ratio of the two things that we need to fully react? So, okay, because this is 0 at the end amount and it starts with 0.400, we know that must be the change of negative 0.400 or negative 0.40. The change of copper must be 1/2 of that, right? That is the ratio. Multiply 0.40 by a ratio of 1/2, right? Sorry, I didn't show my work above, but hopefully you remember that. So this is 0.20, and so this is 0.20. We go ahead and change our pen color here. Sure. Let's do green. I haven't done green yet. So this is not quite the answer because it wants it in grams, not too dissimilar from practice problems we've done in the past. So we multiply this by the molar mass of copper, which is, I believe, 65.55 grams of copper per every 1 mole of copper. Units of moles cancel out. You get 13.11 grams of copper. And this is the answer. This is what the problem's asking for. All right. So hopefully this looks very similar to what we've been doing with the added piece of working with solutions. So for your classwork, which is, I guess, technically homework now because there's no school today, you have some problems that are very similar, where, again, stoichiometry problems, where you have to convert the text into a balanced chemical reaction. This would really say nickel 2, by the way, based on what we've learned in this class. So nickel 2 here. So you're working with some solutions here, and then you're going to answer the questions by converting to moles in some different ways, or maybe working backwards. There might be some limiting and excess reagent problems, as you see here. And again, some limiting and excess reagent problems here. So a little bit different from what we did for the examples, but similar in the sense that it's still stoichiometry and it's still converting from concentration to volume, or volume to some concentration, right? So, okay. So that's the assignment for you to work on. Hopefully you find some time to do that between now and tomorrow. When you come back to campus tomorrow, please make sure to grab your lab notebook so that you can complete your pre-lab. I'll just give a very brief introduction for this lab. So you can read through this all, obviously. It's all here for you. In our previous labs, we've done something called qualitative analysis. That is, we've determined whether or not something is there. When we did the flame test labs, that you might recall, you burned some wooden splints and you told me whether or not a certain metal was present. But you never could tell me exactly how much metal was present. Starting with this lab on Friday, we are going to look at some solutions and try to figure out the amount of stuff present, right? We know that there's some metal present in some solution that I'm going to give you. Your objective is to figure out how much of that metal is present. The reason we care about this is one example of why we care. It's something called hard water. So hard water is water with a lot of minerals dissolved in it. And one of the issues with hard water, if you've ever encountered it, is that it's really hard to lather up soap. You can watch some YouTube videos on that if you'd like. But the ions, the metal ions that are dissolved in the water, prevent soap from lathering up. So it prevents soap from doing its job, essentially. And so if you are buying a house or something, you might want to investigate whether or not the water that's coming into your house is hard or not, because that will add to the cost of the house, because you need to maybe buy some water treatment systems for your house. So what we're going to do is we're going to do a precipitation reaction. So this is the reaction you want to focus on here. The specific ion that we are going to kind of look for in these water samples is calcium 2+ ions. Now, I know that I've written this in a weird way, but really you can imagine that this is calcium chloride. So if you really want, you can just imagine this is calcium chloride, and this over here is sodium chloride, if you want. I haven't written the anion in because the anion doesn't really matter. It can be whatever anions. There's tons of anions in your water anyways. So we are going to be testing for the amount of calcium chloride that's present in some water samples. The way we're going to do that is using a precipitation reaction. So you can imagine that you're mixing some calcium chloride and some sodium carbonate, and when you mix those two things, a solid forms, calcium carbonate. Calcium carbonate's the same stuff that seashells are made of. Now, once you conduct this reaction, that is, if you mix some amount of calcium chloride and you mix some amount of sodium carbonate, and then you filter out and collect the solid, right? You can weigh the solid and you can back calculate, right? You can use stoichiometry to figure out how much calcium chloride you started with. And then that will allow you to figure out the concentration of calcium chloride in your original solution. And if you compare it to some data, right, or some how should I say this? Some some benchmark numbers as to whether or not something is hard or soft. For water, you can make some statements as to whether or not the water needs to be treated or not. So this is the pre-lab, or this is the pre-lab assignment. I'll let you read through the background on your own. There's some safety. I just kind of want you to kind of very quickly Google a couple compounds and write down in your lab notebook if they say that there's anything especially dangerous about them. Here is the procedure. It is 2 days because when you collect your solid, it's going to be wet, and so you don't want to weigh a wet solid because that doesn't give you an accurate number on the amount of compound you isolate. So you have to dry it. So this is a 2-day lab. We'll have a client letter that you'll write in class on day 2. And then there are a couple of pre-lab questions which you need to answer in your notebook. Aside from the name, title, purpose, safety, and stuff, you also want to do your pre-lab questions in there. So there's 2 pre-lab questions here and here. Just some quick calculations. There's a couple of post-lab calculations that you can do as well once you get home after lab on Friday. So this is a pre-lab assignment. I know you probably don't have your lab notebooks, but at bare minimum, you can read through this, and then you can grab your lab notebooks on Thursday tomorrow. Okay, that's all I've got. As always, I'm available via email. Sorry we don't have school today, but hopefully this lesson was helpful. Hopefully you can get through the classwork on your own, and everything will make sense. If you're struggling with molarity and conversions with molarity, make sure to check out some of the homework from the last trimester. All right, take care. I'll see you all in class soon.